Yeah, we're actually going to talk about it in class today too. Now it's an example one of like a difficult reduction that hopefully is enjoyable and also is easy to follow. People wanted to talk about 3-sat more, so I'm going to do another 3-sat reduction. What? What is it, 10 bonus stars? Oh, so this is, I mean, it's sort of, but it's not points. No points on your grade. Yeah, and it also maybe hints at what's going to be on the exam. Yeah. Okay, that's 4 o'clock. Welcome everyone to the final class. Yay. Yay. No? Oh, okay. So sorry if I'm a little lower energy today. By the way, I had to pull an all-nighter last night, so I'm dressed cozy and I'm a little bit lower energy. But we got a lot of review to do. But first, just in case anyone's curious, I wanted to share and take a small moment to respond to some stuff. Not seriously. Interesting things here. There's an amount as a teacher that I can see from over here that I know intuitively, and there's some things that are surprises to see in data like this. I'll talk about what was surprising and what was expected. So flow being divisive is actually expected. I think for some people it just clicks and flows really nice and natural. And for some people it doesn't. Hopefully it's you got a lot out of it still, and you understand the core principles. DP being the favorite is a big surprise, actually. In previous iterations of 311 that I've TA'd, DP is usually the least favorite. So I think that's good. I'm glad that you guys liked the way that I covered DP. Complexity, I think the opposite. A bit surprised by how low it is. I know it's a bit of a tricky topic, of course, and it's difficult to see the point of. I think a lot of people commented that. Hopefully I'll justify that to you a little bit today. We're going to cover it a little bit more today because it seems like people weren't as sure on that. Backprop being low kind of makes sense, although the fact that it's such a disparity between it and DP, because it is really a DP algorithm, is pretty surprising. But it does make sense. I think a lot of people didn't have as good a Calc 3 background, or Calc background in general, as I expected. I think that made a little bit of a distinction there. So, all right. Interesting stats. A couple other things here. It seems by and large the biggest comment was about having more teaching materials. Hopefully this practice exam helps with that. Good to know. I'd like all the feedback has been pretty good. People wanted to go over discussion answers, all of that. People said the homeworks were too hard and too disconnected. That's a fair point. I'm still trying to figure out how to balance it. All of us with the use of AI, it makes it really hard to do traditional homeworks, but traditional homeworks are tried and true and they work really well. So it's a bit of a balance. I tried something here. I don't particularly love how it went. We'll see in the future if it stays or not. Not that any of you are necessarily going to have me again. I also want to comment on the comment about me laughing at students. To be clear, I think it's perfectly fine, and I think it's actually pretty brave for people to comment this on a thing where I see your name, and I definitely appreciate the feedback still. I want to just comment, just because this is, I think, bad signaling for me as a teacher. The times when I've laughed at student answers, I just want to clarify that isn't because I think that they're terrible answers or that you're so stupid I have to laugh at you. It's usually because you're approaching a problem in a way that I hadn't thought of, and you're surprising me. And so I'm having to act on my feet, and I have to think about how to respond to the question. And it's a little moment of, oh, I don't know what's going on. And then I have to figure it out. Just so you know, just if I ever did that to you, sorry, that should be the signaling you take. It shouldn't be that me calling you stupid. If I want to call you stupid, I'll just call you stupid. Cool. Anyway, so any questions on this, by the way, or any comments anyone wants to make? You're free to if you'd like to. But yeah, this is just administrative. So the exam is going to be next Monday in Thompson 102 from 6 to 9 p.m. Okay, everyone just make sure you know that. And it is going to be 3 hours, like we talked about last class. I've written a practice exam, which we're going to be taking today, at least the multiple choice of today. And I really recommend you do it. It took me a long time to write, and I hope that you guys get a lot of use out of it. Yeah, the exam is going to be very similar to this. I'm basically going to use the same template, except add one more question. There's notes on it about the differences. We'll add one more algorithms question, and the problems will, of course, be different. Yeah. Cool. Cool. All right, so I'm going to start today with just a little recap of complexity classes and DP. I know that DP here was wildly popular. It was also commented as one of the most confusing topics still. So it still meant that people wanted to review it. So let's do a little bit of that. And then, of course, in the practice exam, there is going to be a DP problem. And then we'll do complexity, go from the ground up, and hopefully all of you will understand it after this. Okay, any other particular things people want to cover today? Right now, if you say something, I might be able to work it in. Okay, cool. So first up, we're going back to, these are from the notes from last class. We had a couple pages left. We're going to be doing those. So dynamic programming, again, the fundamental idea is to not repeat work. When we're doing our computation, if I would need to compute the same thing I've previously computed, I do not want to do that. Instead, I want to use memory. And somehow using this memory to decrease my runtime is the trade-off that DP algorithms can make. They can choose to store intermediate calculations so they don't need them in the future. And this allows us to get faster runtime at the cost of some use of space. Although some non-DP algorithms use more space still, but in general, we could find an algorithm that's slower that uses less space in general. Okay, and again, fundamentally, when we approach a DP problem, we can structure our memory that we're using, that we're using for memoization or whatever, as an array. The proper formulation of dynamic programming, like in its first formalization, does define it as arrays that are storing the intermediate values or the optimal values in optimization case. And the size of the array defines the difficulty of the problem in DP. But you don't need to worry too much about the formal definition. Just know the core concept. We are storing memory so we don't repeat computation, and we can generally do that as an array, although we are allowed to use other data structures. If you'd like to use a tree or a hash map, something like this, each has their own trade-off in terms of what you can do in what time and how much memory they use. You can decide between them. Okay? Any questions on that overview? Okay. So once again, generally the two components to a DP algorithm are one, how you are storing the intermediate calculations, and then how you are populating this list. How am I iterating over my sub-problems here in such a way that I am able to get my new optimal values or my new intermediate values. And generally in things like Fibonacci, for example, we say that some item in it, let's say opt-I, let's say this is being filled in from left to right without loss of generality, then I can say that this is only dependent on things I've already filled in the left-hand side of it, only those things, some combination of them. So in this particular example, I would just be iterating where I'm going from left to right, filling in this entire array, and every time I fill in one of these elements, I only need to use what was previously calculated to do it, plus some small amount of work. Rather than needing to recompute the entire thing. Okay, those are the two real components. And of course, there are other storage. We can do multi-dimensional matrices. We saw this a couple times. And we can also do other data structures. So just be aware of that. But again, the two main components are how do we cleverly store things we've already computed, and how do we iterate over that to get to our full problem. Okay? Any questions on DP? The other review we're doing of DP today is that I've given you a practice exam that has a DP problem in it. It has some multiple choice and a problem you can do with DP, I suppose. Just say, welcome. Any questions on this? Besides that, I want to spend more time on reductions, so I'm going to do that. So let's talk about the general aspects of reductions and complexity classes first, and then we can do the exam, the practice exam. We're going to do a little activity with it. So here again is a diagram that we've used throughout the class on the complexity classes P, NP, co-NP, NP complete, co-NP complete, and exponential time. Really, P, NP, and exponential time, and then NP complete is it's a subgroup that we care about, and same with co-NP and co-NP complete is another. They're very related to NP and NP complete. Okay, as a reminder of the definitions, here are all the definitions written out here at the bottom. Firstly, we are only considering decision problems when we're talking about complexity classes. That is a problem that that has an answer that is either true or false. Is there a path of length k, not find a minimum length path? Those are so the first would be a decision problem, the second would be an optimization problem. So we're only going to be talking about decision problems. Generally, you can transform an optimization problem into a decision problem by saying something like if I had a minimum number that I wanted to reach, then I could say, does there exist a path of length k? Or I could even count down if there was some enumerable amount and say, is there of k plus 1, k plus 2, whatever. And that can give me my decision problem. All right, so if it is a problem, I'm using this notation up here, A, to mean a problem. This would be something like, is there a shortest path from this to this of length whatever? That is what my problem is, and it has an answer, true or false, and I can say that this problem itself belongs to a complexity class. In this case, P. P is the set of set of decision problems that have the property that there exists a solver which can solve and give you the correct answer. There's exists one that can answer every single possible instance of problem A. So this notation, I've used lowercase letters here, and also you can see that I'm doing like S of A, saying I'm running the solver on an instance of the problem. So A here would be an instance of the problem. So in the example of finding a minimum path, it would be a graph. And it would be every possible graph that fits the constraints of problem A. So if it needs to be a tree, then when I say all A, that would be all trees, for example. Okay? And that is what this instances are. Okay? We'll talk about instances again in a second. Okay. So next up, if it's an NP, that means that there is a verifier, which is a different function that runs in polynomial time, and if it is given a certificate, which is a piece of information, basically you can say handed by God, if there exists a piece of information, such that the verifier is able to use the instance of the problem and the certificate to know the correct answer. But it will only know if the answer is true. So this is a bit of a weird, this is what is the difference between NP and co-NP, is that the verifier only knows if the answer is yes. That is, if the answer to the problem is yes, then we know that the verifier will return yes. But if the answer to this is no, we don't know what the verifier is going to, yeah. Yes.
Should it be an if and only if?
Yeah, sorry. Yeah, no, it is. So, yeah, it is. I was about to correct myself. I just realized this too. So it's if one is true, the other is true, and vice versa. Sorry, yes.
Also, I think we can make it a little clearer, I guess, if we put saying, right, like there exists a certificate.
Yeah.
If and only if. That it's not there exists a certificate such that the verifier accepts if and only if.
Yeah. I mean, okay. So we can put some here, but each of these parentheses or each of these colons act as a parentheses if you'd like. Also, I'm going to leave it for now just because I think it'll look a little too messy, but we can make a note of it later. But this is fine as it's written.
It's pretty hard to phrase.
Yeah, no, it is. It is a tricky thing to phrase. Yeah, sorry. Thank you for the correction. So this is saying if one is true, then the other has to be true, and vice versa. That's only the case for trues. We don't have anything here for falses. Yeah. 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 If we have to prove that it's in P, we would generally write an algorithm. We just write an algorithm that is in polynomial time.
And then for like every single instance, it's always.
Yeah, so we have to prove that for every instance it runs. This is all the thing about proving tight asymptotic bounds, is saying for every instance. Yeah. That make sense? Cool. Yes.
All right, I guess to rephrase, I want to say update, then update is true if and only if there exists a certificate, as in like there exists a certificate is like a single
Yeah.
That's what I meant about like, because it's not like saying like there exists a certificate such that I don't know.
Okay, I'll take another look to see if this is equivalent to that or not. If it isn't, I'll make a correction on here. The important idea, though, there's a value to having this formalization. It can help you with doing some formal proofs, but the general idea still stands, and I think this idea has seemed intuitive for the most part from what I've heard from people here, which is if I give you an instance of the problem, there must exist some sort of information you can give me such that I can check if the answer is true in polynomial time. That's the core thing. The formal logic, I don't expect you to necessarily be using the formal logic. It's there just in case anyone wants to try to formalize things for themselves. But the core idea is just, if I can give you some information, generally a solution to the problem, that gives me yes, then I say that I can verify it in polynomial time, if there just exists one of those. Okay? And that would mean that it's an NP, and vice versa for co-NP, where I can prove that it's false. I have a falsifier that can run in polynomial time. Okay. So in the idea of reductions, again, we're taking every instance. This is something like the A's that I said before. This is like it would be all the graphs that are potentially inputs for this first problem. I want to show that there is some way I can transform them into some other instance of a different problem. For example, a circuit or an array. These sorts of things which could be different, could also be the same sort of structure but changed. And I want to say that there is some way to transform them such that every instance here can become an instance of this problem. So we're mapping each of the instances of problem A onto some subset of instances of problem B. Again, instances here being things like a graph input, being like an array, any of those sorts of things, an arbitrary array, or an array with only binary elements, for example, if that was the type of input we wanted. Okay? And then NP completeness is just being an NP and also being NP hard, where NP hard is defined as having a reduction from every problem in NP to some problem A. Okay? Yes?
So that diagram basically says,
Yes, so this is A reduces to B. Yeah, so this is the same as this statement right here. Yeah. Okay? All right. I think the, yeah. So yes, and this is a very clever proof that we talked about in class but didn't prove in class, which is there exists a reduction to the problem circuit sat. So circuit sat is a particular problem where you have any circuit as an input and you have to return whether or not there exists some input to the circuit, that's some assignment of variables such that it returns true, that it is satisfiable. And there's a clever proof that shows that any problem can be converted into a circuit, and then those problems can then be solved using circuit sat. You see what I mean? Yeah. So that's the high level of the proof. The proof is a little bit more involved, so we didn't talk about it too much, but that's the gist of it. Yeah. Yes.
But then after you have that, you prove that other stuff is NP hard. Some NP hard thing reduces to it.
Exactly. So once we have one of them, which circuit sat was the one that some clever people proved, then we can build off of it, because we can, reductions are transitive. They use the less than equal sign because they are transitive. So I say that, if I had some, then B reduces to C, and I knew that A was NP complete, then C would also be NP complete as long as it's in NP. Yeah. Yes. Okay. Okay. How's this feeling? The high level of reductions. If the nitty-gritty is difficult, that's a different question, but the high level, how's that feeling? Okay. Okay. I think this one is fairly divisive also. Okay. Okay. Noted. We're going to go through a full reduction later on in class. So I think hold yourself for then. Until then, though, we're going to do the practice exams right now. So the way that I'm going to do this, I want to say a couple things about it. So first off, this is shorter than the actual exam by one question, basically. It is very similar in scope and difficulty to the exam. And also, so we're not going to be able to do the entire thing today. We're going to do the multiple choice we're going to be going over in class. And I'm going to let people share their multiple choice answers and an explanation. If you do that, you'll get a prize of some sort. So just keep that in mind. And then we're going to talk about the reduction afterwards. The reduction that is on here is too difficult for the exam. Just to clarify, the reduction problem is too difficult for the exam. The reason it's on here as practice is we're going to talk about it in class some amount, and then also I want you to attempt the problem, and then if you cannot solve it, look up the reduction online. It's a good one to show you what a reduction can look like. It's a difficult one. It's harder than the one you'll have to do in class, but hopefully it will be an educational one. I think it's one that is, once you understand, is very convincing. Okay. So I'm going to give you a little while to work on this. You can work alone or talk to people if you'd like to. I'm going to give you something like 20 minutes, and then we're going to talk through the multiple choice and the reduction at the end. So at least look at the reduction. We don't need to solve it right now. Also, you may notice the bonus is different. If you're a bonus person, you can check that out. There's explanation on it. Okay. Practice exam. Multiple choice right now. Yeah. I'm giving you different names so people don't immediately. They might recognize it. That's the... Continue. I did actually add it last time I did this. It didn't affect anything. All right, don't be too distracted. Motivate. What? No. If you, yeah. It was of the multiple choice. Yes. Here you go. Not focused. Yeah. We're going to be going over the multiple choice and talking about the reduction.
Like a store.
No, it was cute. I live in New York.
Yeah. Oh, yeah. Or Rockefeller.
Yeah, sorry, my thing is weird. I thought this was. I can't do
Check both the ways. 0 1. Bigger a number you put in, and you check both the ways. And so.
Yeah, but what I'm asking is, like, I know that if you want to add changes together, you have to get a power law. I think it's the same.
I'm getting anything that's right.
I didn't see the
I was just thinking.
I was like,
But like, how do you not look at everything? I'm still late. That means there's more edges.
I don't know what to talk with. Okay, sorry. I just like wasn't expecting someone to start.
I just, yeah, just, I think it was under analyze.
It can't be signed. Oh yeah.
They're within the scheme of multiple. Okay, I'm gonna give you like 2 more minutes to discuss with people, but then we're done. Cool.
Factorial just means is it any factorial just feels like n multiplied by n.
This one also. Yeah, we're about to go over the answers.
Perfect.
Yeah, and people who share answers get to spin the wheel. Yeah. Okay, cutting you off, cutting you off. All right, so we're going to go through these answers. I'm just going to clarify the rules on the spinning, just so that it's clear. I'm going to ask about a question. It's going to be first hand up, just first come, first serve. I'm not going to let people. I'm not going to let people answer multiple though, so only one per person. So if you're confident on one, maybe save it. And then you do have to get it right to get the spin. But you still get props for giving an answer. Okay. Are you all right. Who would like to give an answer for question 1? Fine, I'll give it to you. Utkarsh had his hands up the entire time. Yeah. What? It's B? Who thinks that it's B? Raise your hand. Okay. It is, in fact, B. Correct. So the logic behind this is basically... Oh, yeah. Explain it. It's fair. That's multiple choices, yeah.
I knew it wasn't A because that's a stupid x power 5, x power 5, x power 10.
Yeah, exactly. We can stack exponentials that way, yeah.
If you add them, the upper bound should be g of n.
Exactly.
When you subtract them, the upper bound is g of n, but the lower bound does not. It should be f of n. The lower bound should be f of n.
Not necessarily for the last one. So the problem with the last one is, imagine if we had n to the 5th and n to the 5th. If I subtract them, I get 0, even though it is upper bounded. So I can do things like that. If they're the same order of magnitude, you could even yeah. So that you can remove, if it was like n to the 5th plus 4, and then this one's just n to the 5th. If I subtract them, it's just 4. So subtraction doesn't maintain this actually. Cool. Good answer. Yeah.
It's actually wrong to say it's upper bounded by f of n. Like,
Yes.
3 of f.
It could be true, but it is not a necessarily true statement. It isn't that this statement up here implies that. The only one it implies is B.
Why is B true?
B is true because g of n is growing faster than f of n. It's growing more. It's growing at least a scalar multiple more than that, so it's going to converge down to 0 actually as we go to n to infinity. So it will eventually be constant. Cool. Yeah. All right. Anyone else? Yeah, there will be some cutoff point where it's always less than some number. If I just pick some number, because it goes to 0. Yeah.
An example why C is not necessarily true.
Why C is not necessarily true? Sure. If I had f of n is n, and g of n is n to the 5th. If I add them together, then I have n to the 5th plus n, not upper bounded by n. Yeah. All good. Yes. Question? Oh, are you doing for question 2? Sure, I'll give it to you. I give it to him. Okay. He does get a spin. I'll do the spins at the end, though. I think I'll do 5 group batches of 5. Yeah. Question 2. Yep. A. Who thinks it's A? It is in fact A. So this is exactly what we did in merge sort. This is when we take our 2 sorted arrays, we take the lowest out of them repeatedly, and that because they're each n over 2 length, we only have to iterate n times. We only have to do that n times. I guess I answered that part for you, but hopefully you know it. Okay, sure. I'll give you that to you on that one. Any questions on this? There are ways that we could combine them slower, but there is a way that we can do it in O of n, and we've seen that quite a bit. Okay, cool. Question 3. And I saw you first. I'm going to read it again just so that everyone is under. Under what restriction would each of our max flow algorithms run in the same asymptotic time? We've given bounds on each of them. When would they be the same? Yes?
I was thinking E,
Okay.
and my reasoning was that Edmund Karp is O squared, and Ford is EV squared,
Yeah.
and typically there are more edges.
Yeah.
So if you know that there are less, you can just
Yeah, so if we were to have this condition, or if we have this condition, then because we have Edmund Karp is VE squared and Denix is V squared E, we can replace them, we get V squared for each of them. The problem is that this does not do much for our Ford-Fulkerson. So Ford-Fulkerson can still have unbounded error or unbounded runtime because it is dependent on Fmax. So this restriction is insufficient. There could be another restriction that would give it to us. Anyone else want to answer? I think I saw your hand first. So
Is it D?
D. Who thinks it's D? Oh, good on you. It is in fact D. So it is D. The secret to this that you might notice, so there's two parts of it. One is that the capacity of the minimum capacity cut is something we've already established is equal to the maximum flow. So the capacity of the minimum capacity cut, that is the capacity that goes across some cut and is the minimum of such capacity, is equal to Fmax. So if we say that Fmax is theta 1, then we can think about what that means. That means that the maximum flow is some constant number, meaning what would be the runtime of Ford-Fulkerson? It'd be OV, or no, OE, sorry, yes, OE. And then the others are always going to be a minimization over those things. So if we had, it's going to be minimization over its original bound and also this new bound. I suppose, actually now I'm considering there could be other restrictions where they wouldn't be equal in here, but this is definitely the closest answer. Because all of them, by bounding the maximum flow, all of them are going to be able to run in O of E time, which is very fast for any of these algorithms. Okay? Yeah, so it's ignoring the possibility, like some subset of the problems, we would have, V is equal to E or something like that, then be O of V, but they are all still equal. I think it's still fine. Yeah, it would still be fine. It would still be fine. The DFS in Ford-Fulkerson would also be O of E, or O of V, sorry. They would all be equal. Okay, yeah, so that's sort of the understanding here. This is, again, testing a very similar thing to the previous exam, which is understanding when these runtimes are good. And for Ford-Fulkerson, it's when our Fmax is very low, we can have very good things. And all of my other algorithms were still lower bounded, or are still upper bounded by that same runtime. Yes? So each of them, so you can just imagine Edmund Karp. So the proof that gave me that Ford-Fulkerson runs in Fmax times O of E, right? The proof that got me that, it applies exactly still to Edmund Karp and to Denix. Basically, in Ford-Fulkerson, I say, I take any augmenting path, and I apply it, and I might have to do this a bunch of times. For Denix and for Edmund Karp, I'm still finding augmenting paths, and there still is an upper bound on the number of them that I need, but each of them add new restrictions on how many of those I need to find. Basically, how many iterations I need to do. And those iterations are different than Fmax, but they are still upper bounded by the Fmax amount. because I will still be adding 1 max flow per time I augment. So I'll only need to augment F max times, no matter my algorithm, if it is one that does augmenting paths. So because all of these algorithms are doing iterations that are increasing the flow by at least 1 every iteration, the amount of iterations they can possibly do is F max. So all of them have that same initial bound. And for all of them, finding their paths is also O of E. Yeah. Okay. Question 4. I saw yours first. Give a tight asymptotic bound on this. Okay, who thinks it's A? It is in fact A. It is in fact A. So this is one that you may notice is difficult for you to apply Master's theorem to. I think it is a good thing to know. Master's theorem is a useful thing, but it is not a catch-all for all recurrences and all runtime analysis, and it's important for you to see some examples where it's not. So what's happening here is that we will notice n factorial is a very high growth function. It upper bounds a lot of things. It grows very, very rapidly. And because of that, we'll notice that we have the same amount of like overall size in each layer. So I have 2 copies of things half the size, but each of them is going to do significantly less work because n factorial is going to be much, 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 much smaller for a number that's half the size. Think about the difference between 3 factorial, 4 factorial, 5 factorial. The growth is extremely fast. Yeah, so n factorial is going to be the dominant term here. There's an example of a sort of recurrence that looks like this, where it's very top heavy. This is n factorial, and then this would be, the next layer would be n over 2 factorial plus n over 2 factorial. And you can work out that this is always going to be smaller than that by an order of magnitude. So we can keep saying it gets smaller and smaller and smaller, and then so the top term is the dominant one. Okay, cool. All right, hands down, hands down, hands down, hands down. When I say it. Question 5. I saw yours first. What? Prims. So yeah, I think people were eager at this one because people were confident on this. Yes, so prims, could you describe prims to me very briefly?
It creates like waves, right?
Calling them waves, I haven't called them waves, but I think it's fair to say we grow a tree. So we start at some node and we take the smallest edge and we connect the next one, and then we chop anything off that would create a loop, and then we continue to do that. We just have a little growing set. And the local greedy decision we make is just the lowest weight edge each time. Cool. All right, can the 5 people who answered this come up front real quick? Yeah, you get to spin the wheel now. Yeah. All right. Hey. All right, you ready? All right, come here. There you go. Go for it. You want a good one or a bad one?
Should we?
No, it's fine. Aww.
All right,
Terrible.
Who wants my candy?
Candy's in the bag here. You get a choice of either chocolate koalas or sweet tart ropes. Koalas. There you go. Sorry, it's a little squished. The exams crush it. All right, cool.
Will you spin for me? I'm sick.
Okay. All right. Oh. You worried? Oh, is it? Congrats. Nice. But it's not chocolate koalas, so.
I need that.
Okay. By the way, if anyone gets a prize from this, you can message me on Piazza or email, and I'll keep track of it. Cool, ready? Go for it. Oh. A tepid clap. Yeah. Good. Okay, go for it.
I don't need
that. Tepid clap.
Can I give that to my friend?
Maybe. Yeah, you can ask me later.
I'm gonna regret doing this.
Yeah? There are a couple bad ones. No one's got them yet. Oh! Pick someone here. Pick someone right now. Just point at someone. Yeah, okay, get up here. Okay.
Wait, what is give a review? That means you recommend something?
Yeah, just something. Yeah. Yeah, now he gets a -1. I think the icebreaker is definitely the worst one, actually.
Yeah, no, I was so scared of doing getting that one.
You'll see if it happens. Make sure to email me. Okay. All right. What a friend. Okay. Question 6. I think you had it up first, yeah. Exactly. So the question, if he has proven that he has an algorithm that runs in polynomial time, that solves a problem that's known to be in NP, what has he proven? He has just proven that A is in P. He hasn't proven anything else. There's no reduction happening. There's also no, NP is a grander class. So any problem in P is also in NP, but not every problem in NP is in P, perhaps. We don't know for sure if it is or isn't. So all he's proven is that it's in P. Yeah, comment? Okay. Just being quick on the draw. All right. Question 7. That was very fast, actually. Okay. Yeah. Okay, who thinks it's B? It is in fact B. That is the point of the forward pass. I'm glad that everyone recognizes that. Yeah, so we are storing them for future use. It's not that we're calculating derivatives in the forward pass. We're just storing up things we might need in the future. Cool. Can't be up ahead of time now. Question 8. I think back there. Behind you, Amanda, sorry. Yeah. Yes. I think it's B. So the question is, okay, why do you say that? Mm-hmm. Yeah. I'll autocomplete for you. I think that you were going the right direction. Yeah. So we talked about it. It's pretty directly just something I've said. That's also probably why it's hard for you to phrase it. Yeah, we don't want to repeat computation, and so to not do that, we are going to store stuff. Correct. Cool. So that's B. Next up, question 9. I think you were a little too early on the draw. I think Sunny did get it next, actually. Yeah. C. Okay, you want to explain? Okay, yeah. So you do that. You can also just see here that this becomes X and not X becomes 0. Becomes 0. It has to be false. You can also just write it as false. And then if I say that something implies something that's false, this is an example of contradiction. If you can just identify that, you also can do contrapositive this and say that 1 implies P. It's an equivalent thing to just say P. So P becomes true. But you can just notice that this is a contradiction. I'm saying something is not true implies something that is definitely false, means that my original assumption is false, meaning that the original statement is true. Yes?
Does this work the other way around?
What do you mean the other way around? If I had 0 implies not P? That tells me nothing. Yeah, sorry. Yeah, you can reason out why. What an implication says is when I am true, then you have to be true. It's like that's the direction that it works. Yeah. Yeah. Okay. And question 10. I think you got it. Yeah. B. So okay. So quite a part on this, by the way. Circle each. You can circle multiple things. Here, lower your hands. I'm going to do it again. It is multiple also. So, question 10. I think you did get it this time. Yeah. A, B, and C. Do you want to explain? Mm-hmm. Okay, so it is, you probably have identified it as independent set, the independent set problem from class, which we did prove is NP complete, and something is NP complete if it is both NP hard and NP, so all 3 of these must be true. Is it possible that D is true? Raise your hand if you think it's possibly true. Is it possible that I should also circle D? What would it mean? Ready, hands down. I'll give a spin to someone who answers me this concisely. What would it mean? No hands yet until I finish speaking. What would it mean if D was true? I think Alex, I saw you first.
It would be P equals NP.
So this would imply P equals NP. So if this were to be true, then P would be equal to NP because we would then have shown that an NP-complete problem is solvable in P, which means that all of NP is solvable in P because it's the hardest problem. We could just do our reductions and show that everything is solvable in P, and then this would all collapse to P equals NP. And we don't know if that's true. That, again, is the thing that if you prove, you get $1 million. Okay, cool. Next 5, come on up. Or 6, I guess. I said that someone will get down for that last thing, too. All right. All right, go for it. Oh, no icebreaker. Dang.
That's really funny.
One dropped quiz. Cool. There's only 15 quizzes, so it is kind of a substantial amount if you miss too many of them.
Oh, okay, candy.
Yeah. There you go. You get the sweet tart ropes. They're pretty good. They're my
I love these.
yeah. They're mine and my wife's favorite actually. Yeah. I think I'm going to get rid of the candy now. Sorry, your odds went up with both because I'm out of candy. Sorry. Drop discussion. All right, cool. Tepid applause. Tepid applause. All right, here you go. Oh. All right. So you guys can move away from the spotlight. All right. So first, introduce yourself. Your name.
Hello everyone, my name is Sunny. I'm a sophomore.
Okay. Yeah. And what is something good that's happened for you this semester?
This semester?
Yeah. Just anything. Eat a good sandwich. Something really
Yeah.
good. Right? Yeah. You ate a good sandwich.
And drink Coke every meal.
Nice. That was good. Cool. Awesome. All right. Thank you, Sunny. All right. Get on up here. You don't care for this?
That was good.
There are actually a lot of points, by the way. Yeah. Yeah, fair enough. More icebreakers. We want everyone to get icebreakers, right?
It's gonna be me.
Oh, oh that sucks. Okay. We may spin a little bit more. I'm planning to stay here a little bit after class, and we may do a little bit of this after class too, if you want to stay. What? You have to get it to find out. Yeah. Okay. So, I'm going to look briefly at this problem just so that we can maybe get it set up a little bit. So for this problem, how many people actually looked at the other problems, by the way? Okay, real quick, just read them. I'm going to give you like 1 minute. Just read them so that we'll go through them again, but I just want you to read them and parse them on your own first. Okay, I'm going to cut you off there, just so you have a chance to see what it's like to parse the problem before we talk about it. Cool. So for this one, anyone want to give a suggestion for the approach? So just to repeat the question a little bit in plain text, we are given a tree, something like this. This isn't going to be the answer. This is just going to be for drawing. So you have some sort of tree, a binary tree. That is, each one has at most 2 children. And each one of these has some sort of weight, whatever it is. Let's say this is 3, this is 2. And I want to find the path that goes from the root to a leaf that has the minimum distance, the minimum sum of all of the weighted edges. What sort of problem does this feel like to each of you? So who would say that this feels like a divide and conquer problem? Okay, who would say that this feels like a greedy problem? Who thinks this is a flow problem or could be approached with a flow solution? And who would use dynamic programming? Okay, somewhat unsurprising. So there are multiple ways to approach this problem. Dynamic programming is a perfectly good one. If we're doing dynamic programming, can someone tell me how I might store my intermittent values? I'm going with hands, and they're going to get a spin also. Yeah. Exactly. So we could keep it as a tree. So we can also store as a tree, and we can have, for each one of the nodes, we would have the minimum distance to that node. So for this one, it would be, and well, in this case, it would be xi. And the way that we would fill it in is what? How would I fill this in? Exactly. So if I wanted to know what to store here, I would just take the minimum. If this is 2 and this is 5, then I would store 2 here. I take the minimum of them. So it's the minimum path from this node to a leaf. And we can do that, and just repeatedly doing this, we can get through the entire thing. Again, this is something you just have to be careful of what structure you're using here. It would make a lot of sense. It's very easy to describe as a tree, but you have to be careful about how you actually do your algorithm. As you've seen, graphs are not necessarily a very good structure to use in a for an algorithm. They can be a little bit difficult to work with. Yes?
In this specific
No, there could be, so I'm saying to any, not a given leaf, but an arbitrary leaf. So out of all the paths from the root to the leaves, determine, or I don't say it's determine, I'd say find the path that is the minimum length. Yeah. Cool, yeah.
Wait, when is
Yes, so you take the minimum of the weights, yeah. Yeah, all of them are going to have the same degree. They're going to all be 2. Yeah.
Would there be a weight? So
Yes, so you just have to be careful of how you're using your data structure is all. Yeah, so you would have to have a data structure that is a tree, and then you could do tree things on that. But a lot of times people will say, I have a tree, and I'm just going to iterate over the nodes, which how? What order are you iterating over them? You need to be careful of things like that. Yeah.
So in this case, you would check every leaf, and then you go.
Exactly. You'd start at the bottom and then you'd work your way up. You can maybe notice that you can actually just structure that as basically a recursion. So I'm just going to, for each one of these, I'm going to set its value equal to the minimum of the other 2 with a recursive call. So if I were to say, how do I set this one? Or I'd say like opt of this node, right? Opt, this is just node I, is going to be equal to its 2 children. So it's going to be the minimum of a recursive call on its children. So opt, this is going to be like, I'll say I.left and I.right, right? So it's going to look at the 2 below it, and then it's going to do minimization. This is going to be my loop, and then I can just recursively do that. Yeah, opt I.right. Cool. So something like that. And so the key components of a DP algorithm, as we said, is how I'm storing it and how I'm iterating, how I'm filling them in. And generally, some sort of minimization or maximization is very common to do something like this. You just have to be careful about your data structures and make sure that it does actually work. Cool. So that is roughly this. You then have to prove the asymptotic bounds on this. If we're doing this dynamic programming solution, you'll notice we do one operation for each one of these nodes. We just do one minimization. And you can do your counting like that. I'll let you attempt it on your own, though. Cool. and you do also need to prove correctness. This is something that I know a lot of people have had difficulties with in the class, and it is a difficult thing in general, but I do expect you to be able to prove algorithms. That is a core component of the class. If you're having a lot of trouble with that, look at some examples, come to office hours, any of those things. Do know how to do proofs though. Yes? You can use induction. So there are generally almost any one of these proofs you want to do, you'll be able to do either through induction or through a contradiction. And you can basically feel out which one is better for you. It isn't necessarily going to be that one of those two is the best way to prove it, but that's going to be a very safe bet, is that one of the two will work very well. Dynamic programming, I would say generally, if you have a recursive call, doing induction makes a lot of sense. Yes?
Why do we need to store the intermediate solutions?
It can, yes. Yeah. So we don't need to necessarily do it as, so everyone is phrasing it as DP. We don't need to necessarily do it that way. In fact, there are ways to do it with all of the other techniques that are reasonable. You're just pointing out that we have a divide and conquer solution, basically. And yes, we do. So there will be, on the exam, there will be a problem that is open-ended like this, that you can use any method you'd like to do. It may be that dynamic programming is the optimal way. It might not be. It might be that flow is the most natural way. It might not be. I will leave it ambiguous, but I'll try to make it as approachable from as many different angles as possible. Yeah. Exactly. There are other ways to do this problem. Yes. Yes. You could do it as flow. You can do it as a reduction to a different polynomial time algorithm if you wanted to. I don't think many people would prefer that option. Yeah. You can do. You could do. Yeah. You do a reduction from it to 3-sat, solve it in 3-sat would actually be right, but it would give you an exponential time algorithm. Okay. Possibly exponential unless you prove p equals np. Yes. So proof by cases is not a very robust way to prove in general. So there are some situations where I can say, here are all of the situations I can run across, and here's how I perform each one of them. Each one of them I'm fine. Doing this sort of proof by cases is okay. I'll say generally it will be more natural to do either a contradiction or induction, and you have to be very careful doing proof by cases because you need to make sure you're capturing every single case that can appear. In problems that are simple like this, it's not too bad, but it's just it's a scary thing to prove that way sometimes. I have had to write proofs like that, but it's generally not the best. Okay. Any other questions? Yeah. So I could store it as a linked list. I could store it as a graph. It depends. If I wanted to store it as a graph, I would need to be careful because I could blow it up to be, v by v, which it doesn't need to be because it has most degree 2 of each of these nodes. But I could store it in other different ways. I think storing it as an array, storing trees as arrays is a natural way, or you can do it as a linked list. All of those are reasonable. Yeah. Yes, the edges have weights. You could store it in lots of different ways. An array, I would say, is a less natural way to do it. You're more likely to run into errors doing that. Yeah. Okay. Yeah, but sort of by the definition of DP, it could be stored in an array. Basically, anything can be stored in an array, but it's just, is it a good structure for it? Same questions that we've had in data structures and all of that. Okay. And then the reduction. So I want to talk about this reduction a little bit, and I'm going to give you verbally the reduction. I'm going to write it on here also, how you would do the reduction. And I'm going to prove it lightly, but I'm going to leave it as a thing for you to work on as practice. I'm going to give you the idea, and basically I want you to act as a verifier and verify that my given solution is in fact a good reduction. And that'll be your practice for this problem. The actual exam will have an easier reduction. This one is a little bit difficult. But you will have to do a reduction, just 100%. That will be on the exam. Okay, so this problem is going to be the subset sum problem, which is a different one than the one we've talked about. This is the canonical subset sum problem, SSP. And the way it works is we're going to be given a set of numbers. There's an unordered set of numbers, and we need to determine if there is a subset of those numbers. That is without repeating, so I'm just choosing some subset of them that sums exactly to a given number. So for example, if I have that x, the input is 133, then it would be true when k equals 6, because I can choose a subset 3, 3. But it wouldn't be true for the numbers 5 or 9. For either of these, I need to have duplicates of these numbers, which I can't have. Okay? Everyone understand the problem? So the problem is just have this list of numbers. Is there any combination of the numbers that sums exactly to some number k? And it's a decision problem, yes or no. And first we need to prove that's an NP. Anyone want to give a shot at that? Yeah? Yeah, so just give me a subset, and then I need to check, 1, is it actually a subset of the original array? And 2, does it sum up to k? And if both those things are true, then yes, the answer is yes. And we've proven that it's an NP. Okay? Understand that? Again, we're basically given the information of here's a subset, and then here's a solution, basically, and then we can check. Okay? Yes? Yeah, so you'd also need to, that it can be checked in polynomial time. I sort of breezed past that because I thought it would maybe be a little bit easy to spot, but it's a good point. It's definitely something you need to prove, which is doing this check, going through my array. There are n numbers. It only takes me O of n to check each one to make sure that it is, in fact, a proper subset. And secondly, to add them up is, again, O(n) time. I'm just adding them. It's O(n) additions, which is definitely polynomial. Cool? Cool. Yeah. No, good catch, good catch. Next, write a mapping function. So this is going to be a little bit tricky, but I do want to, this is going to be tricky on this problem, but I do want you to try it. And I'm going to give you the starting framework of this, and then I'm going to give you the gadgets that we're going to use. So first off, we're doing a reduction. Here we're doing 3sat to SSP. So that's going to be 3sat is going to polynomially time reduce to SSP. Okay? What that means is I need to take an arbitrary instance of 3sat. So an instance of 3sat is something like so. We've been using this verbiage quite a bit, but I'm just going to make sure that we're all on board with what it means. A 3sat instance is going to be a set of clauses, clauses C1 through some Cn, each of which is going to be going to be 3 different variables, it's just x, y, z, that are all ORed together, sorry, x or y or z. And then I'm going to return, the output of this should be the and of all these clauses, C1 and C2, all the way up to Cn. We have to have that all of these have at least one of its terms true. This is a circuit written in 3CNF form, which is conjunctive normal form. The special things about this form, the reason that we use this form at all, is that we can convert an arbitrary circuit into this in polynomial time, and it's a subset of all possible circuits. So it is like an easier problem for us to do a reduction generally because there's like fewer problem instances when we write it this way. We have a more restricted problem, so it's easier for us to do translations here. Anyway, so we have one of these instances, and we need to convert this, an arbitrary one of these, into an instance of SSP. So an SSP instance is going to be some set of numbers. So it's going to be some, it's going to be some set of, some set of numbers, sorry. Yeah. It's going to be some set of numbers, x1 through xn, let's say here, even though they could be different numbers. So use n here for both of them. And I need to determine, is there there exists some subset such that the sum of all of the elements of S, I should really put that there, that's fine, is going to be equal to some value k. So this is the instance, right? And we need to somehow convert from an arbitrary instance of this into an instance of this where the truth value of each is true. That is, if this is satisfiable, if there is a way for me to assign these variables such that this is all true, then there has to be some way to find these subsets that gives me a sum of k and vice versa. Here I would also like to point out a useful property of this. So this is a problem in the quiz feedback that I got. A lot of people commented on how complexity feels pointless. It feels like a useless thing. And just a general comment on theory. I'm sure Tomas has had people say this before about computer science theory. Theory is very important, actually. It's something that has been the foundational backbone of almost all of our big developments in computer science. The very first, like the Enigma machine that cracked the code, that was sort of like the first big computer that did a difficult problem, was entirely written on pen and paper first. It was entirely based off all this theoretical understanding, and it built to this very useful thing. Same has been true of artificial intelligence. Same has been true of many, many, many things. And this, if nothing else, is a cultural touchstone in theory. It's a problem that a lot of people have pointed at complexity theory and said, this is important for us to make new discoveries. We need to know how all of this behaves. Secondarily, it does actually have a real practical purpose too. If I'm trying to do a problem, right, say that my boss says, hey, I have these numbers, maybe they're like client list numbers or whatever, and I need to make sure that they can sum exactly to this number. Hypothetically, it might be a little bit more obtuse and that, a little bit more difficult to transform into this problem, but I might run into something like that in the real world. And I might bang my head against the desk trying to make it, if I have a data set that's enormous, right? Let's say I have 1 billion people, hypothetically, 1 billion entries in my data set. I might be, or maybe 100 billion, something like that. I might be that I really do need an efficient algorithm. I try running my algorithm, doesn't work. It might be after a time I say, okay, I don't know if it's possible for me to do this problem quickly, but I'll just keep banging my head against it. This is a way for us to say, yes, it is a hard problem. Yes, it is a difficult problem, and it might be that I can't do this. It might be that I can't solve this problem in a reasonable amount of time. Maybe I need new restrictions. Maybe I need a new problem. Maybe I just don't work on it, and I think about a different problem. So this is a way for you, in like practical terms, you might actually need to realize that a problem at least is not polynomial, that it's not easy to solve in polynomial. Alternatively, there are times that you can come across situations where you have a hard problem like this. Say I have this problem, and it takes me a really long time coming up with an optimized solution. It's very difficult and finicky, and it ends up being pretty slow. And instead of doing all that, I could have converted it into a different problem. So in this case, 3SAT would have to be converted into this other problem, and then I can solve it as the other problem. And it turns out that some algorithms, or some problems, for example, 3SAT, while they aren't actually proven to be polynomial or not, can be run very, very quickly. We have very optimized solvers for these. So if you run across one of these NP-complete problems, there does exist some way that in polynomial time you can turn it into 3SAT and solve it as 3SAT instead. And so knowing these problems and knowing that sort of thing is a good piece of vocabulary to have. Even as a software engineer, even if you are going into machine learning or something like that. I can tell you ways that this has come up in machine learning, by the way. You saw one bonus problem I did actually was related to that. But it is actually an important topic. It's a shame that we had so much dislike of it. I'm going to chalk that up to maybe me not being very clear on the explanation, but it is a very important topic, actually. It's a very useful topic. It's not going to be day-to-day useful, but it is important to the human race and to computer science. So if you are someone who jives with this is an important area of research. Yeah, anyway. Cool. For this problem, I'm going to just give you the outline of how we do the conversion. This is not going to be answering this question, by the way, just because I don't have much space. Here's how we're going to do the conversion. So we're going to have some clauses. C1 equals, let's say, x1, or I'll just label them all like this, or z1. Let's give this a not. What we're going to do is we're going to have some number of clauses. Let's say ci is equal to xi, or yi, or zi. I'm just labeling them like this just to make it a little bit easier for me to understand. What we're going to do is we're going to construct some elements such that we want them to only be able to add to some particular number if there's a satisfying assignment. And the way we're going to do that is we're going to have each one of our clauses, let's say C1 and CI, we're going to have a table. We're going to have each of the clauses, and each one of the variables will be a term on here. So let's say this will be like x1, this will be not x1. Then we'll have some amount of other elements. This will be xi, not xi, let's say. And we'll also have, yi,